All right, welcome back. So at this point, we're ready to uh, talk about your fourth test now. We've concluded all the material for this unit. So the first thing that we talked about uh, was 10.5 with the comparison test. Specifically, the one we're interested in was the limit comparison test. Remember what the limit comparison test does is that allows us to compare our series to another series. For example, say we had the series the square root of k over k cubed plus k squared. This would be a very difficult problem to apply the. This would be a very difficult problem to apply the integral test to. But remember, the ideas for the comparison test is we would say, well, let's look at what would happen as we get very big in the k department. The only thing that would matter in this numerator is the k. The only thing that would matter in the denominator is the k cubed. So that can be simplified to be 1 over k squared inside the square root, which could be simplified by taking the square root of both things to 1 over k when k gets really, really big. So we would compare this to the 1 over k sequence. We would compare this to the 1 over k sequence. So remember what the limit comparison test said. So it's been a little while, so let's just pull that back. Is we would set up a limit of one sequence terms over another. And then we would say if those terms go to anything between 0 and infinity, then either both converge or both diverge. Right? If the limit goes to 0 and the denominator converges, then we'll be able to say the whole thing converges. If the limit goes to infinity and the denominator diverges, then we can say it's certainly sure that the numerator must also diverge. Okay, so once we have a series to compare it to, like 1 over k, we could then consider the ratio of those two things. So we would compare, in this example, the square root k cubed plus k squared. We compare that to 1 over k. Now we know 1 over k diverges. So we're kind of hoping to see that this limit of this stuff is going to approach some number. So that we can say, since this one diverges, we assume we're guessing ours is going to diverge as well. But we do have to actually prove it. So here's how I'm going to accomplish that. I'm going to remember that 1 over k, as k gets really, really big, is the same as the square root of 1 over k squared. So this would be limit, as k goes to infinity, of the square root of k over k cubed plus k squared. And then 1 over k is the same as 1 over k squared, but now it's being divided. So we would multiply by its reciprocal. It would be k squared over 1. So now we have a limit as k goes to infinity of the square root of k cubed over k cubed plus k squared. At this point, we can say, hey, all that's going to matter is the k cubes in the top and bottom. So we would have limit of 1 over 1, square root, which would be 1. So since it goes to 1, and we know 1 over k diverges, we know that our series diverges. Right? And that's how the limit comparison test worked. Remember, the other possibilities with the limit comparison would be If it goes to 0 and the bottom converges, then we would say it converges. If it goes to infinity and the bottom diverges, then the top diverges. And that's how we use that test. Okay, if it's equal to some number, as it was here, then they either both converge or both diverge. And so here we find out that this series is similar to the harmonic series, which we know diverges. Okay. All right. Then we talked about alternating series in 10.6. Remember, there are three things that we have to be sure of with. I think it's two things that we have to be sure of with alternating series. So if we return now to 10.6 with the alternating series, our result was required two things, and that is that beyond a certain point, the terms of the AK sequence need to be non-increasing or typically decreasing. But non-increasing is enough. Right? Terms have to be decreasing, so they need to be getting smaller. And the limit needs to, of the AK terms, needs to go to 0. And those are the two things that we need to have happen. If that's the case, then we know that the alternating series, which again could either be -1 to the k plus 1 with your series, or -1 to the k, either one. Both of those will be alternating. This series will converge. Okay? So if the limit of the underlying sequence goes to 0 for the most part, it's going to converge. Again, you do have that little technicality, but really isn't going to be a big deal for us. Okay, so that's how we check convergence. All right, so as an example, we looked at this series, right, and realized that the limit as k goes to infinity of that stuff goes to 0. It's clearly getting smaller, right? Bigger powers of that stuff are definitely getting smaller. But that goes to 0, right? And the way that I was able to do that is, in this case, 4/5 k, I can rewrite as e to the ln. E to something negative is going to go to 0. If it's a positive exponent, it's going to go to infinity, depending on which one we're dealing with there. And so, of course, that goes to 0. Of course, it also converges because it's a geometric series. So we can actually say what it converged to in that example. Right. As another example, if we looked at the series here, alternating series, k sine of 1 over k, we check, does the limit go to 0? And actually, we discovered in that case it doesn't, so it diverges. Okay, so the limit went to 0, it's decreasing. And again, I actually showed it here, but for this decreasing thing, you can just look at it and say, hey, if I just take that 1 over k to the 4th root of k, and k is getting bigger, of course this is going to be smaller stuff every time. So we don't have to like formally prove the decreasing part. If we can just observe that, and then we know that the limit definitely goes to 0. So that's an alternating series. The other thing we talked about in 10.6 was absolute conditional convergence. Absolute conditional convergence. The big examples were these two series, 1 over k and 1 over k squared. Right, 1 over k diverges, but its alternating series converges. 1 over k squared converges, and its alternating series also converges. So if the absolute value converges, we say it converges absolutely. If the absolute value doesn't converge, yet the signed series does converge, then we say it's conditionally convergent. Conditionally convergent. So you'll be checking through those two possibilities as well, absolute and conditional convergence. And the big place where that often gets used is also with the ratio and root test, which is what we ran into in 10.7. Ratio and root tests. And again, you can see that definitely as well. Absolute conditional convergence alongside the root and ratio test out of 10.7. 11.1 is where we talked about Taylor polynomials. Remember the process there. The nth degree Taylor polynomial would be the sum. K goes from 0 to n, right, of the kth root, or sorry, the kth derivative. My mind somewhere else. Kth derivative evaluated at our center, divided by k factorial, x minus a to the k. Right. So you'll be asked to construct some Taylor polynomials. None of these on your test would be anything that's going to be extreme where you're going to spend 20 minutes computing the derivative. These will be ones that you should have too much trouble computing derivatives of. Okay. And then, of course, using that to approximate a function. Right, using that to approximate. Again, if you go back through the notes, we did some different examples there. Okay. 11.2, we talked about power series. The big thing with power series that I'm worried about on the test is just given a power series, find the interval of convergence. And we did a lot of other stuff in 11.2, but I won't be directly testing that. So we did some other stuff with building new series by, substituting stuff in to an already known power series, integrating and doing derivatives of power series to get new series. But the one thing I'm worried about out of 11.2 is finding this interval of convergence. Okay, given a power series, find its interval of convergence. Won't be asking you what it converges to or anything like that. Just finding this interval of convergence. And then 11.3, we talked about Taylor series. So you'll be asked to find a Taylor series or Maclaurin series. Find Taylor series. And of course, being able to determine, once you have a Taylor series, when it converges. We also talked about binomial series. So we'll ask you a question or two about computing the binomial coefficients, and possibly a question about setting up a binomial series. And by the way, the binomial series, you see it in the homework. May not have, it actually is expressed incorrectly in the 11.3 homework. It's actually expressed incorrectly. So the last three problems are binomial series. So you might have a question asking about a binomial series. Setting up at least the first few terms of a binomial series. And you can do that using the binomial coefficients. And that's what we were just talking about a little earlier, where we had our binomial series, right? All right, and we used it on the one hand to approximate square root of 1 plus x, first four terms. And then we actually used binomial series also as a way to convert or to compute the series for 1 over 1 plus x. We realize that's a binomial series with p equals -1. Right, and we quickly saw that this thing, -1 choose something, was always just an alternating sign. And that's how we were able to get our series there. So, okay. So that's kind of in a nutshell your test, a little brief overview of what is on that. Good luck, and if you have questions, please ask me. Please, if you run into questions as you're preparing, please always feel free to ask me.